Hey, we're back. Happy Monday. So we are on week 10 of the semester. So we're all very excited that this is our sort of second checkpoint of the semester. And I do suggest everyone go to Canvas. And if you haven't done so already, definitely take a look at the listing for this week 10. I mean, first off, even before we look at that, if you look at our schedule, we're really getting close. This semester is a little compressed, and it's going to be over before you know it. And I think ultimately, looking at how Project Part B is going, I have goals, I have aspirations for what I want Project Part C to be, and it is the same assignment as it was in a more typical semester. But I also recognize that the semester is just going to end at some point, and we'll have done our best, and we move on with life. Um, but we're on week 10 right now in checkpoint number 2, and the two things there that I think everyone would want to be able to see are the exam 2 review slides, which we'll walk through somewhat briefly today, and then as well as just a separate set of practice exam questions for exam number 2, and we'll also look through those as well. There's a couple good questions on that. There's a couple good sort of, I call them rejected exam questions on the slides. As I had mentioned previously, I refactored the exams quite a bit this semester just to make them a little bit more amenable to the Canvas way of doing things. And I think I've learned a little bit through that process, and the exam questions are a little bit better for exam 2 than they were for exam 1. But for that same reason, the practice exam looks quite a bit different. It looks like a almost not a different course, but a different style of question, because that was just paper and pencil, scribble down your thoughts and draw some things within 50 minutes, and there's no drawing for our Canvas style exams. There was a question about Project B, something about the byte addressability of the register file, but the register file is just that word addressable component. There is still that same issue where MIPS for the memory, for the data memory, assumes a byte addressable data memory, and our memory module that we just provided for you is a word addressable memory, and you do need to be aware of that. Where life would have gotten really complicated for Project B is if we were wanting to support the store byte and store half word and load byte and load half word instructions. Then you'd really have to very carefully think about how we actually store the right values into our memory. We could have done it. It would have been an extra couple of weeks. But even for our store word and load word instructions, we do have to be very aware that our processor data path is generating a certain address, which is assuming a 32-bit byte addressable address. But then our data memory is this 2 to the 10 entry word addressable component here, and you have to do a little bit of that shifting of bits to get the right inputs into our address field there. And that's something that was already there as part of Lab 4, but I think you would have been just fine in Lab 4 if you kind of ignored that, to be honest, and you could have gotten Lab 4 complete and get 100% on it. Now, when we're doing that direct comparison to Mars instructions on a cycle by cycle basis, you have to do it right. So that's something that you can look back at some of the old Lab 4 discussions where people were asking about that, or that's certainly very fair game to discuss, for Project Part B. Um, how do I actually interface properly with my data memory? It's not hard. It's just something that does have to be done exactly right. So those are the results of the poll in terms of how people are doing on Project Part B. This is partly for my own edification, but then also I think partly so you can see um, where you are in relation to your peers. I think that's okay. I would put people in that orange bar, the most common response, as even being a little bit behind at this point. You could spend weeks kind of putting everything together. At some point, you have to get ideas to paper and paper to VHDL, and then test and make sure your basic assumptions are correct. Because there'll be bugs no matter how long you take on that stage. And so you might as well get to those bugs, see what's happening now, and then you can continue to revise and refactor. If you're still hammering away at that spreadsheet, I allowed for multiple choices here. It's okay if you're still hammering away at that spreadsheet, as long as you're also doing somewhere else along these lines. If you're only on the spreadsheet right now, um, some people are saying that this is going to be a very busy week, and for you, it does need to be a very busy week, I would say, to catch up with where people are. And I do expect a lot of hiccups with debugging the framework itself and getting to a point where you understand what it's trying to do. That's fine, and just trying to understand what the framework is trying to do, get those first few instructions working, and then once you're at that point, I think you'll be in a good place, and it's just a matter of continued test generation and testing and debugging, and you'll be okay. And any bugs you run into at that point are bugs that, if you chat with the TA or chat with me or post on the forum, you'll have a pretty good chance at getting past those bugs if you're in that place. With control instructions being that extra wrinkle, but everyone should be getting to that point this week in lab where they have add instructions working and they're just trying to figure out, how do I support these additional instructions throughout. Anyway, so it's good that people are getting there, but time is running out in terms of the amount of days remaining with regards to that. So, in terms of our checkpoint number two, everyone should probably have maybe a copy of those slides open, because what we'll do is the same as what we did for the first review, which is we'll go through some of those questions together. Then I'll break you up briefly into rooms, and as we break out into rooms, you can hopefully just chat with a random classmate, and it will be a randomly assigned classmate, and hopefully they're here, and hopefully their audio is working, um, and just discuss your thoughts on these questions. And I think I can always give you my perspective on the answer to every single question. I've been doing that all semester long, so let's do some peer sharing as well today, and I think that may help provide that additional express additional insight that maybe just listening to me isn't providing. So the exam, just for those who weren't entirely sure, is this Wednesday. So in 2 days, it is quote unquote in class, right? So it's in our virtual class, and so that does mean I will be kicking off the exam, at 8:50, 48 hours from now. So be here and be ready for that. It is a 50-minute timed exam, as the first one was also intended to be. I am still messing with the Canvas quiz settings because I really want to avoid what happened last time, which is it auto submitted in the middle of a question, and then for some people, all that progress on that question got lost. And I think there's a little bit of maybe inherent unfairness in that, right? If you were working on a multiple choice question on the last question, you were fine. But if you were working on, in that case, a coding question and it lost all your progress on that question, just based on what question you happen to be working on, that's not analogous to the paper and pencil example, and I didn't think that was fair. So right now in Canvas, it's listed as something like a 2-hour exam or a 200-minute exam. It is still a 50-minute exam. I can determine how long you've worked on the exam. I will ask everybody when 9:40 rolls around on Wednesday to hit submit. Finish the sentence you're typing so that it doesn't end in the middle of a word or something like that, and hit submit, and it'll be 50. Maybe for some it'll be 50 minutes and 7 seconds, and that's okay. But that's the plan for Wednesday. So we'll be using Canvas still in the similar way, but hopefully it'll be closer to the analogous situation of paper and pencil, and everyone's kind of, you know, drastically scribbling something down at the very end to try to get partial credits. It is open book and open notes again. I think it's a fair question to what extent that's helpful. Having the entire book in front of you probably isn't that helpful on a timed exam like this, but having your own sheet of notes, your own distillation of what you think the core concepts were for this middle third of the semester could in fact be very helpful during that exam. There are fewer questions on this exam than the previous one. It is 10 questions. Um, and I think I've timed it out correct. I do think you should be able to get 100% on this exam if you're prepared for the material. Looking back on the first exam, there was probably one too many questions, maybe one and a half too many questions. This should be okay in terms of time limit for it. You still have to work at a good pace, and you still have to know this stuff, right? When I give you a homework assignment, you have a week to figure it out, and so you can be figuring out as you go. In this one, you have to basically know, and now you're applying your knowledge for the exam, and so the timing is assuming you know the material at that point, and then from within that assumption, I think the timing is okay for this. I didn't harp on this as much for exam one, but an exam, even in this virtual, weird, mixed up world we live in, is your own individual work. Um, Please do not collaborate. Just please don't. I'll probably still be able to catch you. I guess if you're sufficiently clever, I won't be able to catch you. And I just don't want to deal with it, and you don't want to deal with it. And get the grade that you yourself have earned. Be fair. If it's not really fairness to me, but be fair to your classmates who, by and large, are working individually on these things. Um, so don't post questions online, don't have an open Discord channel. There's technology that allows me to kind of in an Orwellian fashion monitor your webcam and audio and make you take pictures of your room to show that you're by yourself. And I don't want to do any of that stuff, right? I want to trust you. That didn't work very well in the first exam. So please, I guess begging is my next approach. And also the acknowledgement that I know the material at a sufficient level that I'll be able to catch you. So please don't do it. That is kinda just begging, I guess. Okay, in terms of the topics, that we are covering, there should not be any surprises on this exam. Exam 1 probably had some surprises just because it was our first exam and in a new format, and, exactly what I was gonna ask maybe wasn't all that clear. In general, though, when I think of what is a fair exam question, I review back and look at what did we do in class? What did we really spend our time focusing on in any of those in class examples? That does change from semester to semester. So I can share with you older exams, but then they're not necessarily as representative of this semester's discussion and this semester's focus area. But that's my first thought is what are things that I've expected that you've read? What are things that I've expected you worked on in terms of homeworks generally? And what are things that we have discussed in class and really focused on that's that's my inspiration for determining which exam questions make sense. So that's always the case. So there should be no surprises in that sense, assuming some level of engagement, throughout that middle third of the semester. And in terms of the topics that we've covered, there have been three major topics. So we started off looking at that CPU performance topic. The textbook brings that. Out in the very beginning, but it's a very abstract when it's in the very beginning of the textbook. I wait until a little bit later in the semester when we already know a decent amount about the MIPS ISA to now talk about performance, because now it starts to make a little bit more sense in terms of what it means to have different CPI values and how we can estimate processor performance based on instruction mix, because we know what the instructions are generally doing. So understanding the basic performance equation and how we can manipulate it, keeping track of the units with regards to it, knowing what CPI is and how to calculate it, understanding Amdahl's law, recognizing that a question is an Amdahl's law question. We spent some time on that. And then I've been a little bit of a broken record this semester, talking a lot about critical path, both in the abstract, what does it mean to have a critical path in a circuit, as well as specifically for the processor designs that we have been exploring. Where is the critical path? How can we at least, generally identify it, if not an explicit value? Can we know it when we see it in terms of a path through a design that we ourselves are building? And that's a topic we have spent quite a bit of time on this semester. We also talked about computer arithmetic. Actually, quite a bit less of that than I usually spend in a typical semester. But you've also had that experience in the lab, right? So while the in-class discussions were a little bit high level in terms of arithmetic, you had that project part A experience where you had to really show it and build it for the adder, for the general ALU, for supporting things like a set less than instruction, as well as for your barrel shifter. Those are things that not only do we cover in class, did we not? We had some homework questions on digital logic and ALU design. You've also now gone and built it in the lab, so those questions are definitely fair game. And then with regards to processor design, we spent a lot of time on the single cycle data path and control, and also in the lab. Based on that poll, you're about halfway to truly getting that working. If you have your spreadsheet done, and if you have your diagram in a shape where you feel pretty comfortable about it, you're in a good place with understanding single cycle data path and control. The same kind of in lab exercises you're having to do for that, which is I now have a new instruction. And it was a homework question as well. I have a load upper media instruction. I have a textbook data path that doesn't talk about load upper immediate at all. What does it mean for me to be able to now implement that instruction? What new control signals are needed, if any, or can I use existing control signals? What should the value of all the control signals in my single cycle data path be? And how do I wire this up? It's always add a mux, but what mux do I add and what does that mux do? Those are very much, I think, fair game questions because we've been doing a lot of that homework in class um, and in the lab now as well. And so you should expect questions on that. My goal is always in this class for the second exam to talk more about and have an exam question on multi-cycle data path and pipeline data path. We haven't really We've talked about pipelining based on the quiz on Friday. I don't think we're ready for it yet, and that's okay. So those are two topics that those are explicitly crossed out. There may still be some material here referring to pipeline, analysis and things like that. We just haven't gotten to it. I mean, we've talked about it. You haven't really had a useful homework assignment that's been due yet. You haven't done it in the lab certainly, and in class we've done okay, but not great on it yet. And that quiz on Friday also told me that we need a bit more time, and so it's not an entire win for you, but that we'll eventually have those questions on an exam, but that'll be on the third exam. So for the second exam, in terms of what you are studying and what you are analyzing, you can stop when you get to single cycle data path and control. Um, that's fine. We don't have to have an exam question just because we talked about something last week in class. There was a question in the chat here about rundown of average grade percentage in the class. Yeah, I don't know what that rundown will look like. I'll certainly do it for exam two. I did give some midterm grades for folks. Generally, those who are really worried about am I going to get a C minus in this class, or can I reach that C minus in this class? If you didn't receive a midterm grade report from me, you're doing just fine with regards to that. Um, those who are really struggling in this class are those who are kind of not submitting assignments. So, it happens, life gets busy, but if you skipped 4 homeworks and didn't submit 2 labs, and there's a few of you who are in that category, you're the ones who are in some risk of not getting an acceptable grade in this class. Once we'll have 2 exams in place, I can really analyze and see how things are going. Um, it's always a little harder to answer the question of am I getting an A minus or a B plus in this class? That I have trouble analyzing until really close to the end of the semester. So those are 2 separate concerns. Am I failing the class? I can definitely talk to anyone about that, and the answer is generally no. If you haven't already heard from me, the answer is no. You're fine. You know, we can. Everything is still achievable in terms of grades in this class for you. Are you getting an A or an A minus? That's harder to say. Really depends, in fact, on how Project Part B is going. That's a lot of points, and it depends on how Exam Two is going for you as well. That's a lot of points as well. I don't know how satisfying that is. Yeah, the whole thing's curved, somewhat holistically, and I said in the very beginning, this was day one of the semester. I said I would like everyone to get a 4.0 in this class, or a class 4.0. Um, I don't feel my job is to, sort everyone and saying, well, this person's an A minus and this person's a B minus, and consequently, this B minus person isn't going to be as good of an engineer. I don't think that's the business I'm in, right? I think there's some important concepts to learn in a course like this, and my job is to try to make it somewhat relevant to you and interesting to you, and perhaps I have a little bit of fun along the way, as well as some tears. That's fine. Um, but it's not that strict sorting isn't as important to me. I feel like everyone who is doing their part in this class, who's done the labs, who's gets the projects figured out, who is prepared for this upcoming exam, you have a very good chance of getting an A in this class still roughly maybe 60% of the points are still kind of ungraded so far in this class. So yes, the whole thing is going to be curved, but I really think everything is still achievable if you've been you know, participating in the class to this extent. And if that's the case, you're fine. You're going to be fine. The people who get Fs in this class, and there's some every semester, are those who kind of stop doing their part as a student, and that becomes pretty obvious at the end. Okay, so in terms of where in the textbook, and actually on the exam, I link to just the PDF versions of these chapters. Section 1.4 to 1.10 are pretty important, and then a small part of chapter 3 is fairly important for you, and then you can stop where it says here that 4.1 to 4.4. Um, Opinions differ as to the value of this textbook. That's my little joke, and I had to go and find mine, underneath the table somewhere. Um, I think it's a pretty good guide. I think it's a good supplementary guide. My lecture notes, my rambling 3 times a week is not a textbook. It's not as thorough. I forget things, I have typos and mistakes along the way. It's meant to be, companion material to what we've been covering in class. And I do see that sometimes. I do see, questions sometimes on Discord where the snotty answer, if I was in such a mood or so inclined to do so, would be, well, that's in the book. Why aren't you reading the book? And, maybe that's a lost cause. I do think that would be an effective use of your time between now and Wednesday would be to read through relatively slowly those sections in the book. And if you do so, I don't think there'll be surprises on this exam on Wednesday. So let's before we go into some questions, I'll very very briefly talk about the things that we covered just to remember what was relevant to us at the time that we were covering them. So remembering ALU design, this should be relatively fresh in your mind because we did this ripple carry adder design. Um, and what that means from the single bit level and then that ripple carry chain through the upper level bit. We also looked at, if we wanted to support more advanced instructions that do some parallelism, those SIMD extension instructions, how we would potentially manipulate that ripple carry chain to support things like a byte parallel add instruction. Um, and also when we looked at the shifter, how we would potentially tweak things in the shifter to support different operations as well. One of the practice exam questions talks about that issue. Um, it's hard to say exactly what is, a fair game question on this, but there will be questions that assume fluency in terms of understanding what is happening with the adder, not just the schematic, but conceptually, why is the adding doing what it's doing? What does that ripple carry chain actually do? Um, I think people are generally in a good place there, so I don't expect that to be an especially hard question. I do get the impression that we didn't maybe cover the execution equation as well as I would have liked. Um, but it is an important one. It's important in terms of understanding two big concepts, right? One is that our execution time is generally, or our performance is generally measured in terms of time. So if you get a performance question and it's asking about performance of processor A versus processor B, or optimization A versus optimization B, right? The textbook style questions, it's always talking in terms of time. And then really your challenge is to keep track of the things we know about a processor's performance, which is potentially its clock rate slash clock cycle time, the average CPI or IPC for its instruction mix, and the dynamic instruction count for a particular application of interest. We can modify those things to potentially improve our performance. We can make our clock rate faster, right? When our clock rate becomes faster, that denominator becomes larger and our time becomes smaller. So don't get too mixed up there. That means performance is better, right? Time is less, we are faster. So performance has gotten better. We can also decrease our dynamic instruction count, potentially, right? That's what algorithmic optimizations do. That's what some compiler optimizations do. And then as architects, we also have potentially some influence over the CPI of our processor, right? We even just looking at the single cycle for which CPI equals 1 to these theoretical other designs for which CPI varies based on the instruction, whether it's multi-cycle or not, you'd be given an instruction cycle count per instruction type, a CPI per instruction category. We can balance that trade-offs, and there are trade-offs that we've seen, right? That we can do things like partitioning our single cycle critical path so that instructions now take more than one cycle. One of the reasons we do that is so it makes our clock rate faster, right? We partition our circuit, we can clock it faster. We've cut the critical path into some subdivision. But we've done that, and then consequently, our CPI, if we're not careful, is likely to go up, right? So we have to be very careful when a question asks, what is the performance impact of partitioning our critical path? Well, the answer is I need a certain set of facts to be able to know that for certain. Otherwise, I can answer in the general sense of my clock frequency increase has to more than compensate for the increase in my CPI for my performance to be improved. And if it doesn't, I'll have a faster clock rate CPU that is actually slower in terms of runtime, in terms of performance, than my original CPU. And keeping track of the units of my equation allows you to really make sure that you don't accidentally put CPI in the denominator of this equation or put instructions in the denominator, or is it clock rate or is it cycle time that I put here? Um, You can have it written down so you have it handy during the exam, or just remember to keep track of the units. That in terms of performance, my answer should be in terms of time. And if my units wind up being instructions squared per cycles cubed, that means that I did something wrong in terms of what I put in the numerator and what I put in the denominator. Definitely in terms of things to know. And it can be a little tricky. I think that we kind of distinguish between textbook single cycle data path and lab single cycle data path. They have a ton in common. There's no denying that, right? For the type of questions I ask on homeworks, because they're inspired or sometimes directly taken from the textbook, as well as questions that will be on the exam, I will try always to be very explicit and clear that starting with the textbook single cycle data path, um, that's my exam voice. Starting with the textbook single cycle data path, how do we support X, Y, or Z? Otherwise, the answer is always going to be, well, it depends on what I did in the lab. And so I'm not going to be asking about that. There's enough points for your lab progress. For exam and homework and quiz questions, you can assume, and if I need you to assume, I will provide this figure on an exam. Um, the homework question would say something like the figure 4.31 in chapter 4, modify this mux so that you can now do this operation. Fine. I'll provide you with this diagram, but for this to be, in a time sensitive manner, something that you can appreciate, you really do need fluency in this diagram. And we're getting to the point now based on homework, based on what you've been doing in the lab, that you shouldn't be looking at this for the first time and saying, this does look complicated, right? We've covered this a lot. So at this point, that would be my expectation for you, that we have our 5 stages of execution from instruction fetch all the way back to write back. And even in the single cycle data path, because I won't ask about the other processor design choices here, you should know what all of those control signals do, why all those muxes are there, and how it all gets tied together. A couple quick questions about that. It is complicated, right? There's a lot going on. This is a 300 level computer architecture class, and um, well, it's not simple. Someone asked about memread, and we've talked quite a bit about memread in terms of for the memory design. Do we care about the value of it? Can we always have memread, or should it be a don't care? Memwrite, it doesn't really show the port names here. This would be our write enable for the memory. This signal is kind of going underneath. That would be the read enable if such a thing was necessary on our memory. A second question is asking about this ALU control, where the textbook describes a very specific ALU opcode and function code encoding scheme where there's an intermediate control signal that drives a separate control unit to generate your ALU local control. And I really just barely touched upon that in class because I don't think it's that important. And that's not how you're generally doing that in the lab. So I won't ask, does ALU control signal of 00 mean add or something like that? What would be relevant to us, and we did it for quiz questions on this topic, would be we have this opcode coming in. It's a load word instruction. What is our ALU doing? And that you should know. Load word instruction is doing an add immediate operation, right? So whatever this gets encoded as, I don't care. That's different for everybody's implementation, but it is doing an add immediate. So whatever this is, it corresponds to an add. Whatever mux that corresponds to in your design, I don't care. But it's an add, and not only is it an add, it's an add of that immediate signal. So that value needs to be 1 in our ALU source. That's the kind of fluency I think is pretty important um, as of right now. And then for the load word instructions as well as for the store words, it's not the actual result of the add that we care about. It's the result of the add operation that corresponds to an address in memory, right? The load word and store word is using the ALU to calculate an address. It's a base register plus a constant offset. And then depending on if it's a load or a store, if it's a store instruction, we're done. We have the address field. We actually have to grab the right data from the register file ourselves because we're not using it in the ALU. And that gets written to the memory, and the store word is done. We've written to memory. For the load word, we're not done. We've generated the address. We have to actually do a mem read, and then that value has to go back into the register file. That's the value that we're writing back into the register file. Um, that step, I think I can claim is fair enough game that we have talked about that a lot. Um, you're still doing it in lab. I understand you haven't built that step yet, but you've done a lot of that in lab already, going back to lab number 4. We just are adding that instruction fetch and instruction decode. And so when we talk about the worst case timing, when we talk about the critical path, there's a reason I keep harping on and saying, our load instruction for the single cycle operation is our critical path, is our worst case timing, right? We talk about how there's so many different paths here. You're only seeing some of them, right? Just through our register file, there's so many different paths, right? Because you're muxes and you have the decoders and you have all these wires inside that component. But at the top level, our longest path, our critical path, corresponds to the instruction that triggers all of that logic. That we have to go through the entirety of that circuit to get from instruction fetch to our write back stage. And that's the load word instruction because we have to do our fetch. We have to do our decode and in parallel read from a register file. We have to do our execution for the reason we just talked about. We have to do our memory stage. And then finally, we have to do our write back stage. Whereas every other instruction can skip a stage along the way. And every other instruction, if there was no load word instruction, could get done in less amount of time. But our load word, and we don't know exactly which path along the load word is our critical path, but that rough red wire here is tracing out our critical path. And somewhere along those lines, there's a set of wires and gates that lead to the longest critical delay through our design. And that's what's dictating what we can run our clock frequency at. From register read, which is our program counter read, to register write, which is our reg file write. That's our longest path. We have to go through all that stuff, and that's our critical path. So that's what sets our clock frequency for the design here. So I'm seeing a bunch of questions, and I don't want to get too sidetracked. I know this is important. I think that and I'm glad you're asking this. It's good to know what people are stuck on. It turns out we're not using NAND at all, so that's fine. You can ignore the NAND. But in terms of why is this shift left to here? And I see that there's an answer in there as well. Um, that's in the textbook, so that would be a good use of reading. I think it's 4.2 that talks about how that gets supported in there. That's something we have talked about a few times. So the branch instruction in its immediate field is encoding a PC offset. It's a number of words away, a number of 4-byte quantities away from our current PC plus 4 value. So in order to turn that into a byte offset, because that's ultimately what our program counter is supporting, we're basically, you call it a shift left to, concatenating 2 zeros at the least significant bits. We're kind of just getting a savings in terms of the encoding of the instruction that way. In that 16-bit field, now we're basically allowing for 18 bits of byte offset from our program counter. It lets us branch that much further away. Those kind of questions are all fair game questions, but that is what I mean when I say fluency in this diagram at this point in the semester is expected. You're not there today, that's fine. You now have 47 and a half hours to get there, and you should try very hard to get there for Wednesday, and then you'll feel a lot better after Wednesday's exam is over. And that is frankly the point of this course as well, right? I mean, to understand data path and control and how we go from high level source to assembly source to underlying machine implementation. Um, I would feel like I haven't done my job if you don't have a decent feel for what's happening in this diagram. So it's both of our responsibilities, but the grading only goes in one direction here. In terms of things to know, you do not need to know the multi-cycle. I mean, you need to know it, just not for the exam on Wednesday. I didn't edit out these slides. In terms of pipelining, in life, you should know what pipelining is, but not for this exam. Same for that. Some rejected questions, so we can go through a couple of these. This one is too hard. So this was rejected for being too hard. So there's a lot of different ways one can implement an adder. And in fact, we didn't really even talk about the carry look ahead adder other than a little homework question that talked about it in some brevity. Um, this is a carry select adder. So the question would be having something to do with understanding how the carry select adder works, and from this diagram, can you explain why this gets better performance than a typical ripple carry adder? I'll call this semester a rejected exam question because that's a little too difficult. But the idea is that can you read a logic diagram corresponding to an ALU and understand what that ALU is attempting to do? For the ripple carry adder, yes, you can, because we've done it. You've built it. You've built it twice now, basically. Can you look at one that you haven't built in the lab and appreciate what it's attempting to do? In this case, what the carry select adder is attempting to do is to we can work from this side of the diagram and make our way leftwards. Is it looks at the fact that that ripple carry is our critical path in the adder, right? We can't get to the next bit of addition until the previous bit of addition is done because we don't know what the carry value is going to be. So the carry select adder is recognizing that there is that ripple carry, there is that critical path, but ultimately that carry signal is either a 1 or a 0. Right? I mean, in terms of what it actually is at runtime, it's one of two values, right? You have two choices what the carry signal itself can be, and so don't sweat it. What the carry select adder is saying is, well, and maybe this is the best one to look at for this second byte. Um, treat it, split up the adder in certain ways. This is splitting it up byte by byte, which is actually not the most efficient way of doing it, but that's one way of doing it. And do two different 8-bit additions for those middle bits of our inputs. Do one in which we assume the carry in is 0, and do a separate one in which we assume the carry in is 1, because we know ultimately it's going to be one or the other. One of those two values will be correct and one of them will be wrong. And eventually, we'll be able to figure out which one is correct. And with that knowledge, we can select using a mux and actually get the correct output out. And the reason that that's faster is because now, in fact, we can do all these additions in parallel. You can actually do the upper bytes of addition before the lower bytes of addition are done, because you're doing them assuming the carry in is 0 and also doing it assuming the carry in is 1. And then we do still have a critical path because eventually we have to know what the actual carry signal was. That'll take a certain unit of time. We don't have to wait that long to get our final result back. If the original ripple carry adder takes roughly 32 time units of latency for whatever that gate and wire latency would be, we can do so in 12 with this kind of carry select adder. You can actually do it in significantly fewer. Adder design and multiplier design is still kind of an open area of study and evolution. Our goal is to have an ALU that you can debug in a feasible amount of time in the lab, right? But you can make your adder significantly faster. And there's always a couple groups each semester whose goal is to maximize the clock frequency of your pipeline or single cycle MIPS processor. The adder will be part of that critical path, and so these are the kind of things that you can explore. And I'm happy to help you explore as well. Maximizing your critical path, minimizing your critical path, but maximizing your clock frequency. So another rejected question. This one is only rejected because I've asked it too many times and I got bored of it. So there's nothing wrong with it. So add the store constant instruction to the single cycle data path below. For this to be a valid exam question, I would have to provide you more context than that, right? I can't just say add an instruction and not tell you in a textbook style of way what that actual instruction is doing, specifically. Let us assume that this instruction takes the immediate value, sign extends it, and just stores that value into the register file at the selected address. So I don't have my tablet working here today. So it'd be like store constant into T1, comma constant value, 16-bit hex value or integer value that fits in 16 bits. This is a good example in that I like asking these kind of questions. We asked a few on a homework already. There'll be a question very similar to this on the exam on Wednesday. So store constant takes the constant and stores it into the register file. How would we implement that? Some of you may look at this and say, this is obvious. I know exactly how to do that. Let's break out into a room for 2 minutes and discuss with a partner. We have a lot of people here, so let's somebody's going to be left out if I do it this way. Anyway, we'll break out for 2 minutes and load, store. Yeah, that's a valid question. I get to decide what the instruction does based on its name, though. So, store constant into register file is what this one's called. Write constant into register file. How would we support that? Do we need, and the kind of things you'd be answering would be, do we need new muxes? Do we need new control signals? Can we, how do we support this? The answer tends to be the easiest way to provide an answer to this is to annotate a diagram. You won't be able to annotate a diagram on the exam. I could have done that, but that would have been a real headache with uploading images and things like that. Describing via just simple sentences, how would I support this instruction is the kind of question you will get on Wednesday. So a couple people dropped out due to fear of breakout rooms. It happens every time. I'm going to create these and we'll just take 2 minutes, discuss with a new friend today what you're seeing for that. How's it going? Can you hear me? No one joined your room. Unfortunately, in the middle of the class, when I do those breakout rooms, a certain percentage of students are just, asleep at that point. I did realize though, one second. Yeah, this isn't going to work all that well because it is currently getting recorded here. Let me see if I can mute on my end here. I don't know if I can. Nope. Yeah, I mean, we can discuss it. Okay, so this will be a version that just this isn't a time to share your innermost deepest thoughts because this is being recorded for posterity's sake. At least my side of the conversation is so it will sound like I'm talking to myself. So what are your thoughts on store constant here, which is storing it into the register file? And that's the right thought process. And I'll reiterate that if I were to ask this on the exam, I had better do a better job of explaining exactly what the instruction does. If it was a store into a memory, then there's definitely some muxes that are needed here because normally there is no path that takes a constant, takes the immediate, and connects it to memory. We would just have to add that path, right? If it was store into memory, I said in class just now it was store into the register file, in which there's not a direct path, but there's an indirect path, right? We can take our immediate offset, sign extend it, and maybe just add 0 to it. And then we have that value that we can then connect back into the register file. Um, so if it's write constant instead of store constant, that would be supported without any additional muxes. If the instruction was instead to store that constant into memory, well, we would need some way to specify what address, but there would need to be a mux for that write data port as well. So your thought process is correct. What does it mean to store something? I had better provide that context so that people are aware exactly of what that means. In this case, I said it means write it to the register file with a little bit of just treating it as a special case of existing instructions. That path looks like it already kind of exists to get back to the register file. Okay, excellent. Let me check on everyone else here. Thanks. Okay, welcome back. People are filtering their way back. I hope you met a new friend, someone you maybe didn't know until today. Um, some valid points that were pointed out in the breakout room that I was a part of, and which also will get recorded. If you want to hear one half of a conversation in a breakout room, you can review the video later. Is that yeah? The name of the instruction is ambiguous, and it's pointed out in the chat as well. If it was store a constant into memory, I would definitely need to provide more context here, right? Where in memory, where's the address getting encoded? If it was store constant into memory, we could do it. We would just need a way to get from this immediate type directly to the right data port. We would need to instrument that. That would be adding a mux there would be part of your solution. What I said before I sent you all off into the breakout rooms, um, I do wonder what percentage of the breakout room was one person was not there and one person didn't have a mic. I don't know. But what I said was it was stored back into the register file. So there has to be a destination register that's specified somehow. It would have to be, that RT field, right? Because we're using the entire immediate field. So the register destination would certainly be 0 for it. And then it was just to take the immediate value and store that directly into the register file. And there is a path, right? We can go from our immediate, we can sign extend it. It goes through the ALU first, but then there is a path back to the register file. And so there's lots of things we could do with that value. If we just want the constant itself, we could add 0 to it. That would be the easiest way or most straightforward way to implement this via the existing instructions that we have. And then that would be an example where you would be supporting this instruction with basically 0 overhead in terms of re-architecting your data path, right? It would just be a very specific set of control signals corresponding to this instruction that would drive the existing muxes that you have there. So your answer would have to speak to that. What new elements would be needed? Do we need a new mux? Where would that new mux, if we needed it, be connected? And then what would be the values of all the other control signals in your design in order to support that new instruction? But I certainly agree with those who are saying, what exactly is this instruction doing? On the exam on Wednesday, if there's enough context to answer that question. That was also rejected because I didn't provide that question here. This is the type of question that I like to ask. It was discussed quite a bit on homework, or there's quite a bit of homework questions relating to this type of question. I like it because it is a little bit summative in terms of what we learned in the first third of the semester. I'm not asking you to write any code. I won't ask you to write any MIPS code on Wednesday. But your fluency in MIPS is something that we're somewhat expecting at this point in the semester, right? So to be able to answer this question, you have to be able to do two things. One is you have to be able to trace your way through MIPS code. How many instructions does this take to execute? And secondly, you have to be able to connect that back to the performance equation. We're actually running out of time today. So I will have my office hours today. So there is plenty of time. Whoever wants to come join me, we can work through more homework or more of these rejected exam questions. But take a look at this material as well as the other material posted on Canvas. Run through the questions, and Discord's a very good chance to ask those questions. I think it's fair game for me to be able to debug any of your answers for those questions between now and Wednesday. But there's one that we just left it off on. This is a pretty critical question to me because it ties everything together. Can I understand how many instructions this takes to execute? Yes, if you had the time, you probably won't be able to copy paste it very easily off this PDF, but I could type it up, could put it in Mars, and can execute it. That'll take too long on the exam, right? So you don't want to do that for the exam. You should be able to just via just annotating determine, well, there's a loop here. Can I figure out, given a certain input, how many times this iterates, or what the steady state is for this code as it iterates? Can I then connect that to a CPI table and get a determination of what my performance would be of this resulting processor? That's connecting multiple concepts together. That's a fair game question as well. We had a couple of homework questions that did exactly that. The other sample practice questions also has a question very similar to that. If you're not very comfortable with doing that, you have some time to become more comfortable between now and Wednesday. Otherwise, come join me in office hours today, or just post as you have questions on general. And I'm really hoping everyone does well. on Wednesday. Selfishly, I'm hoping everyone does well. It's easier to grade if everyone understands the concepts, and I can grade that much quicker if that happens. I'm just hoping that in this difficult semester we've had so far, that we're doing the best we can, and ultimately you're picking up the core concepts of this course. So let's leave things here for today. Wednesday's the big day. I'll see everyone bright and early on Wednesday, and good luck.